Hello, welcome to another module in this massive open online course. So, we have seen the concept of a matrix inverse and how to evaluate the matrix inverse. Let us now start looking at applications of matrices. Now, predominantly one of the main applications of a matrix is to formulate a system of linear equations and to solve the system of linear equations, right. So, let us look at a broad class of applications of matrices where we use the matrix inverse, specifically where we want to use the concept of the matrix inverse that we have just learnt. This is to solve a system of linear equations. I think that is important, the linear equations, right, which is essentially you have the system of the form a11 x1 plus a12 x2 plus a1n xn equals b1, a21 x1 plus a22 x2 plus a2n xn equals bn, so on and so forth, and then we have an1 x1 plus an2 x2 plus an xn equal to bn, and so you have the system of n equations, and these x1 x2 xn, these are the variables or basically the unknown. So, you have x1 x2 xn these are your n variables or n unknowns, So, we have a system of n equations and n unknowns, and this is a linear system of equations because it is linear in x1 x2 xn. So, this essentially is your linear system of equations. And why is it a linear system? Because it is linear in these variables x1 x2 xn, right. It does not involve the powers x1 square x1 cube, right. It is simply depends on x1 x2 xn, right. So, this is a linear system of equations because you have n equations, because this is linear, right. This is a linear system because this is linear in x1 x2 xn, and naturally you can write this as, you can put all these things together as a matrix. You have our matrix a11 a12 a1n a21 a22 a2n an1 an2 ann times x1 x2 xn equal to, you can say, B1 B2 Bn. You can call this your n cross n matrix A. This is your n dimensional vector x bar, this is your vector b bar. So, you can write this in the compact form, Ax bar equal to b bar, that is your compact representation of the linear system of equations. This is your n cross n square matrix. Simplest formulation where you have a square matrix. Now, what happens when the matrix is not square? Then the problem becomes more interesting, right? So, in this simple in this the simplest form, we consider n equations, n unknowns, and furthermore, if the matrix A is invertible, right? If A inverse exists, then the solution is simply given as A inverse x bar. This is the solution to the above linear system of equations. X bar equals A inverse B bar. Of course, as we have said, this is relies on the assumption that the matrix A is invertible and A inverse exists. Now, of course, what happens when A inverse does not exist, or in fact A is not a square matrix, that is, you have more equations, less equations, more equations than unknowns or less equations than unknowns, then it becomes very interesting and through this course. But this is to begin with, we can look at the simplest problem where you have n equations, n unknowns, and the matrix A is invertible. The solution is given by A inverse B. Okay. And let us take another example, a very simple example to understand this point. For instance, you have, let us say, the matrix this is the equations, system of equations in 3 variables, right. So, these are your, this is your 3 cross 3 matrix, these are the variables or the unknowns, right, and this is your vector b bar. So, this is your vector x bar, this is your vector b bar, and these represent the equations 7x1 plus 2x2 plus x3 equal to 2, 3x2 minus x3 equal to minus 1, and minus 3x1 plus 4x2 minus 2x3 equal to 3. These are the equations, and the solution is given as A inverse B this is equal to minus 2, and we have already calculated A inverse in the previous module. If you remember, we have already calculated A inverse, and therefore, the solution is simply given as A inverse, which is essentially your matrix minus 2, 8, minus 5. You can look at the previous module to check how to evaluate A inverse 7, 9, minus 34, 21, right, times 2 minus 1, 3. So, this is your matrix A inverse. This is, so I will simply say here, see previous module to see how we have evaluated A inverse, and then you get x bar equals, you evaluate this, and this gives you x bar equals minus 27 38, I am sorry, minus 27 38 115. This is the solution of this problem, of this system of this 3 cross 3 system of linear equations, which is Ax bar equal to B bar, 3 equations, 3 unknowns, matrix A. We have seen it is invertible, we have evaluated its inverse, the solution can be computed using A inverse B bar, and that is what we have evaluated. Now, let us move on to other interesting examples. Of course, this is an abstract example. Let us move on to other interesting practical real life applications of linear algebra, right, the theory of linear algebra and matrices. All right. So, let us start looking at practical applications of this. And remember, this course is applied linear algebra. So, we are not only simply going to look at the abstract or the theoretical aspects of linear algebra, but we are going to integrate these concepts. I think that is the most important part of this course, that is not only look at the concepts, but alongside look at the applications, so as to relate these concepts to the applications, which will help you understand better and appreciate the concepts, and more importantly better understand how and where to apply these concepts that have been learned, right. So, that is one of the important goals of this course, that is to teach linear algebra, but not purely in a theoretical fashion, but from an application perspective. So, there are several interesting, and in fact, that is one of the interesting things that probably we have discussed at some point, that linear algebra is probably one of the most important and one of the most extensively used theoretical tools, because linear algebra, linear modeling arises whenever you have linear systems and linear analysis, and a large number of systems in science and engineering can be represented, modeled and analyzed using therefore the principles of linear systems, which is essentially based on linear algebra, right. So, linear algebra arises where is used very extensively, and applications are numerous, and we are only going to scratch the surface of that. I encourage all of you to look at, further explore many more such applications, I mean even outside of this course, all right. Okay. So, there are several important applications, we have already noted this, several applications of linear algebra, and in particular of this concept of matrices and inverse matrices and the inversion that we have studied so far, right. So, I am just going to simply say the concept of matrices. Now, the first example that we are going to look at is basically in wireless communication or modern wireless system, or wireless system design, you can also say, where for instance all of you must be familiar that the modern wireless systems are basically 4G modern wireless networks. You have the 4G, and in the future you will have 5G, and of course you have also the Wi-Fi. And these are based on a very interesting technology, these modern wireless systems. These are based on what we call as the MIMO technology. Now, what is MIMO? MIMO stands for, so what is MIMO? Multiple input MIMO stands for multiple input, multiple output, And what does this mean? This is a very interesting technology, multiple input, multiple output. What it means is, in a typical wireless system, you have the transmitter, right. So, for instance, let me draw this thing. You have what is the meaning of this MIMO? You have the transmitter, you have the receiver, and then you have these antennas similar to what we have seen. Each of these is an antenna, and what MIMO means is that you have multiple antennas, right, multiple antennas at the transmitter from which you can transmit multiple transmit antennas, and you have this multiple receive antennas. So, you have the multiple transmit antennas from which you can transmit multiple symbols, right, and you have multiple receive antennas from which you can receive multiple symbols. So, you have multiple inputs, that is the multiple transmitted symbols, and you have the multiple outputs, that is the multiple received symbols. That is the reason this is known as, such a system is known as a MIMO system. This is a very advanced wireless technology which is used, as I have told you, in 4G, 5G wireless system, and that makes it possible to transmit at very high data rates in such systems, all right. So, MIMO is an important technology. So, MIMO is a very important technology, I would say very important technology. For 4G/5G, which makes possible to transmit at MIMO is a very important technology in 4G, 5G. It makes it possible to transmit at very high data rates. Now, just to give you a brief background of this MIMO, so we have, for instance, Hij. So, each of these is a channel which we have seen similar to our discussion of the wireless system before, and each channel is characterized by that channel, that is H is characterized by the channel coefficient Hij. This is the channel coefficient between TX antenna, between the RX antenna, receive antenna I and transmit antenna J, for instance H23. This is the channel coefficient between receive antenna 2 and transmit antenna between receive antenna 2 and transmit antenna 3. So, that is the concept of the channel coefficient H23, and naturally you can put all these channel coefficients together and you can make them into a matrix. So, once you put all these channel coefficients together, it becomes a matrix which we call which we call as the which is basically termed as the MIMO channel matrix. Okay. So, therefore, you will have H11, H12, H1 T, I will talk more about this, H21, H22, H2T, HR1, HR2, HRT, right. This is the channel matrix H. As you can see, this is R cross T matrix. R equals number of receive antennas and T, this is equal to the number of transmit antennas, number of transmit. T is the number of transmit antennas, alright. And therefore, this is your R cross T MIMO channel matrix, and this is very interesting. Now, you have the channel, which is essentially when you look at the rank of this MIMO channel. Now, let us look at the rank of this MIMO channel. This has very interesting implication for communication. So, the rank of this we know is less than or equal to minimum of R comma T, number of receive and transmit antennas. And what can be shown is that in this MIMO system, the maximum number of symbols that can be transmitted at any time instant, which basically has a bearing on the transmitted data rate. That is, the larger the number of symbols that can be transmitted, the higher is the data rate. That depends on the rank of this channel matrix, right. So, the maximum number of symbols symbols less than or equal to rank H, which means if your rank H is large, you can transmit a large number of symbols at any time instant. So, the data rate is going to be very high, and that is how it is possible to transmit at very high data rates in 4G and 5G systems. So, rank plays a very important role, rank of the channel matrix plays a very important role in determining the maximum data rate that is possible in a wireless communication system, right. So, that is a very important. So, you can see linear algebra is everywhere, in particular modern wireless communication, to determine the data rate. For instance, what kind of data rate is it possible to transmit, what kind of data rate is possible to transmit at, for instance, by the base station to your cell phone, right. Okay. So, rank determines the data rate. So, rank, larger rank determines the data rate, large rank H implies larger data rate, right. And therefore, once you have the MIMO system, you can transmit a much larger number of symbols. That is basically in the same time and frequency, you can transmit a much larger number of symbols. That is, you can multiplex a larger number of symbols. This property is termed as spatial multiplexing. So, H, because of the MIMO system essentially implies transmit or multiplex a large number of symbols in same time slash frequency. This is termed, and this property is termed as this property of, so this property of MIMO is termed as spatial multiplexing, right. So, this is a very important term this property is termed as spatial multiplexing, and this is a very important property which makes it possible to transmit at very high data rates in 4G and 5G systems. So, this is what makes possible. So, MIMO technology via this property of spatial multiplexing, right, of MIMO makes it possible to achieve very high data rates in 4G, 5G wireless systems. Alright. So, this is the spatial. So, essentially what you are doing is you are multiplexing multiple streams to through space. So, this is basically also termed as the parallel transmission of multiple data streams in same time frequency. This is the parallel transmission of multiple streams, right. So, this is basically spatial multiplexing. And now, let us look at how to design the receiver for a MIMO system. How do you design the receiver? Very simple. Let us look at a MIMO receiver. So, now remember we have this multiple antenna system. Let us consider a special system with number of receive antennas equal to number of transmit antennas equal to R, and let us call these output symbols as Y1, Y2, YR. So, this is your receiver, this is your transmitter, right, and these are your transmit, these are your transmitted symbols. So, x1, x2, xr are the so we are considering a special system in which R equal to number of transmit antennas equal to number of. So, we are considering a special system. We will see what happens if they are not equal later, right. So, we are considering a system with number of transmit antennas R, number of receive antennas R. So, it becomes a square channel, right. So, and these are basically the transmitted symbols x1, x2, xr. These are basically your transmitted symbols. And y1, y2, yr, these are the received symbols. These are the received symbols, and these are related by the channel as follows. That is, the model for the MIMO system is given as y1, y2, yr equals your channel matrix H, which is your channel matrix H11 up to H1T, HR1, HRT. This is your R cross, oh, in this case I am sorry, this is an R cross R channel matrix, right, and this is your x1, x2, xr, plus you have your noise vector, this is your n1 into nr, So, this is essentially what we call term as the MIMO system model. So, this is your output vector y. This is what we are going to use several times in this course. This is your channel matrix, this is your transmit vector x bar, and this is your noise vector. So, you have y bar equals h times x bar plus n bar. This is essentially your MIMO system model, and the different components of this model are as follows: y bar equal to h times x bar plus n bar. This is your output vector, output of the received vector. This is your channel matrix. This is your transmit vector. And this is your noise vector. And now the question is how to, and remember we are considering a special case where this is an R cross R matrix. So remember this is only a special case, this is not a general case, this is only a special case. Okay. Now the question is how to determine the transmit vector x. How to determine x bar at receiver given y bar. This is essentially for this case where r equal to r, if now you can see h is invertible, then x hat, which is basically what we term as the estimate of the transmit vector at the receiver, that is the recovered transmit vector at the receiver based on the output symbols or the observed symbols y bar, that is given as simply h inverse y bar. Okay. It is like solving a system of linear equations, but mind you this is valid only when r equal to t and h is invertible. This is what is termed as the ZF, or it has an interesting name. This is termed as the zero forcing receiver, or essentially it is equalizing. One you can also think of it as an equalizer, right? It is essentially, although it is not typically called as, sometimes also it is called as an equalizer, typically it is known as a zero forcing receiver, that is it is basically essentially inverting the effect of the channel. But however, remember this is only valid when r equal to t and h is invertible. Now what happens when r is not equal to t, in particular when the number of receive antennas is greater than the number of transmit antennas, that discussion is going to be very interesting, which we are going to see in the course, I mean in the course of this MOOC, right. So that discussion is going to be there, very much going to be there. So what happens when r is not equal to h? So let me also note that what if r greater than t, then I would say things become interesting. We will see this. We will see this in the future modules, right. So this is the zero forcing receiver also, and note that this is, I mean not the zero forcing receiver, but this particular application, that is your h inverse y, this is valid when r equal to t and h is invertible, alright. So, essentially, so this is one of the I mean these are very interesting applications of linear algebra, right. So, essentially the idea is to convey to you the sense that what we are learning, these different concepts, these are not general, these are not just abstract theoretical constructs, but these are really powerful concepts and techniques that have a lot immense applicability in practice. For instance, we have just talked about one such application in the context of MIMO technology, multiple input multiple output technology, that employs multiple antennas, for instance at the base station and at your cell phone, and naturally when you have MIMO, so the channel becomes a matrix kind of a channel. So, and therefore linear algebra and the principles of matrices, concepts related to matrices such as rank, the rows of the matrix, columns of the matrix, and all these become very important. As we have already seen, the rank has a very important role to play, because that determines the maximum number of symbols that can be transmitted. Larger rank implies larger number of symbols, which implies very high data rates, right. The matrix inverse, that basically for an R cross R equal to T system, that basically can be used as a receiver to recover your transmit vector. So, all these concepts have very powerful applications, and we are going to see many such applications of these techniques, of these concepts in linear algebra as we go through this MOOC, alright. So, with this motivation, let me stop this module. We will keep discovering such applications in the subsequent modules. Thank you very much.